So let's continue with the rest of chapter 2. So for section 2.7, the application of static field, the very last example is example 2.8. In the previous two examples, we use the prescribed charge distribution to calculate the electrical field distribution using the Faraday's law. Similarly, you can use the given current distribution to find the required magnetic field distribution using the Ampere's Kirchhoff law. So in the static field condition, there is no time variant part. So the equation, the Faraday's law, which involves the closed loop integral of magnetic field intensity, the currents, and the time derivative of electrical flux density. However, in the case of static field, the time varying power of electrical flux density goes away. So you can simply relate the magnetic field with the currents, that is, the currents enclosed by the contour. That is where the magnetic flux density need to be evaluated. So here is our problem geometry. You are looking at cross-section view of a cable, of a current cable. So the currents runs in which direction? Runs in the z direction. Runs in the z direction. And here is a cross-section cut on the xy plane. So it's basically a cylindrical conductor running in the z direction. 所以这个是一个沿着 z 方向延伸的金属沿着 z 方向延伸的金属。所以你现在看到的是在 xy 平面上面，也就是 z 等于0的平面上面的横截面。那你可以看到这个点点是电流的分布，它是一个均匀分布的状况，所以它的电流分布写作 J 等于 J0， 然后它是均匀分布的。而这个我要提醒各位的是，均匀分布的在导体内均匀分布的电流，只有在静场状况底下会出现。只有在静场状况底下会出现。所以假如你不是静场状况，而是一个交流电的话，会发生什么事情？假如是交流电的话，你的电流分布会跑到表面，也就是会集中到金属的表面，中间就会没有。那这个东西我们在第4章吧，第4章会再讨论一下，叫做 skin effect 肌肤效应那个是来回往复的电流，交流电流会发生的状况，也就是在导体内部里头没有电流所以你去看有剪过电线吧，对不对？所以你看到一般的电线，其实它都不是一根金属只有你在做那个电路学实验的时候，你才会看到一根几类抽般的那个电线金属线为什么？因为假如你的电流都是在外围，都是在 circumference 的话，那它的电阻其实跟你的那个电线的粗细就没什么太大关系了但是假如是直流电的话，它的电流是均匀分布，所以粗一点的那个金属线，它的电阻是比较小的所以一般你剪下去，电线剪下去，你看到的都是一捆的细线，对不对？因为一捆的细线，它的 circumference， 它的周边边缘会比较多，然后那个中心的部分是相对比例就少所以利用周边比较多 circumference 比较长来去减少那个用一捆金属线的形式来去减少内电那个金属电阻 ，OK Alright, so for this case, which is static current, so it's distributed uniformly in the conductor, and we would like to find the magnetic field everywhere in the neighborhood of this conducting wire, current conducting wire. So here, see there you have two red dash line. So you can so say that's two examples. Okay, one is we would like to know the magnetic field intensity outside of the current conducting wire. But at the same time, you can also derive the magnetic field intensity within the current conducting wire. There are some basics we can learn from this configuration. That is, the magnetic field associated with this current, static current, is in which direction? Is in the phi direction, which can be guessed or can be estimated using the right-hand principle, right? So based on the right-hand screw, you know the magnetic field is pointing this way, which is in the phi direction of this cylindrical, in the z coordinate, cylindrical coordinate system, all right? And will there be a difference between the magnetic field within the conductor and outside of the conductor? Yes, similar to the example we discussed yesterday. For the calculation of magnetic field intensity, all the current included within the contour counts. So on the other hand, so for this larger circle, this larger contour, all the currents that's passed through this conductor should be taken into account to find the magnetic field intensity. On the other hand, how about the magnetic field intensity in this smaller circle, in this inner circle? Well, only the current that is enclosed within this contour counts. All the other current that is placed outside of this contour has no effect on the magnetic field intensity at this contour. This thing is true from a macroscopic perspective. However, it's probably not true from the microscopic perspective. 所以我要跟他讲说，假如你是在外圈的话，当然所有被包含进去的电流所产生的磁场都必须要纳入计算。但你可能比较困惑的是，那这个比较小圈的，它内部有包含电流，外部也有电流。那根据我们昨天的例子，我们可以推论我们至少可以猜得到，内部有所包含的电流在这个红圈圈里头所包含的电流是要被计算在内的。那在这个红圈圈、小红圈圈外面的电流，它可以不用被计算在计算磁场的时候不用管这个红圈以外的。好，那这件事情对不对？从数学上来讲是对的。那从物理上来讲呢？物理上来讲，这边的电流一样会对于这一个红圈圈造成磁场的影响，没有错。只要你个别一个一个来去看的话，但是总体来看，所以我们说巨观macroscopic 巨观来看的时候，这些在红圈圈外部的这些电流分布，它所产生的磁场，在红圈圈的不同位置都是互相抵消的。好，所以它不用被计算在内。好，所以我们的磁场计算，只要计算这个红圈圈内部有被包含的电流所产生的磁场就够了。OK， 外面它其实是会互相抵消的，就像我们昨天讲的重力场，或者我们昨天的 example 讲的那个空壳假如月球是空心的话，它的内部是没有重力的那我们昨天讲的电场，外部的电荷也一样不会对内部的位置的电场产生贡献。OK， 好，那搞清楚这件事，那剩下来其实就只是数学上面的计算。All right， 好。So because of the symmetric property, we know that the magnetic field intensity produced by this current, which is aligned with the z direction, only produce magnetic field in the phi direction. So H has only the phi component. So you can write the magnetic field intensity H as H phi, which is a function of R due to the value of according to the value of R, it can be, of course, larger or smaller number, and H phi is in the phi direction, as you can imagine. And we will substitute these known factors into the ampersecution law in static field. That is, you have closed loop integral of H and current calculation, where S is enclosed by this closed loop contour C. So let's write up the left-hand side first. So you need to carry out a closed loop integral on this circle where the radius is R. So here for the line integral on this circular contour, the integrand is the differential length becomes R d phi. Again, I would notify you that d phi is only a difference in degree. It's not a differential length. So to be a legitimate differential length, you need to times the R, the radius at your observation point. All right. And because the integrand is in the phi direction and the differential part is in the phi direction, and the dot product cancel them out, so you have an H phi, which is a function of R, is invariant to the phi variation, so it can be regarded as a constant, so that it can be pulled out of the integration. So you simply have an integration of 1 over constant 1 in the phi direction. So it becomes 2 pi r, H phi r. Of course, at this point, we still don't know what H phi is. We don't know the function. However, we can look up to the right, to the other side of the equation. That is the computation of the total current passing through this cross-section area. And it's a surface integral, so it's of course the result of two line integral, which are integration toward the phi direction as well as to the r direction. So here you write up the integration for this surface. The surface direction is pointing to the z direction, so the differential surface is r d phi dr, r d phi dr. Okay, you need to have two differential lengths. And the limits are from r equals to 0 to r and phi equals to 0 to 2 pi. And again, because this thing is a constant, so the integration is relatively simple. It's simply the product of j sub 0 with the surface area of this circular region, that is 2 pi r squared. And however, you need to be careful about the limit, because when the observation point R is greater than A, and because the current exists only in the region of R smaller than A, so the limit is from R equals to 0 to A. On the other hand, if you are looking at some observation points within this conductor, then the limit of your integration on the r-axis is r only, which is smaller than A. So you have two results for the two cases. When the observation point is outside of the current, then you have j sub 0 pi a to the square. On the other hand, if you are within this cylindrical current, you only account for the currents reside within your observation point. So you have a j sub 0 pi r to the square. Okay, so once you have the right-hand side and right-hand side, you can put them together and get the expression for h phi. That is, will be j sub 0 r over 2 for r smaller than A, and j sub 0 a to the square divided by 2r for r greater than A. Okay, so you have these two cases. So what are the consequences? The consequence is, if R is smaller than A, you have magnetic field intensity proportional, linearly proportional to the distance R. On the other hand, if R is greater than A, then the magnetic field becomes smaller and smaller as the observation point R becomes larger and larger. And from mathematical expression, the magnetic field intensity is inversely proportional to the distance R. And you are encouraged to draw the equation graphically, draw the equation graphically, so that you have this graph. So say when R is smaller than A, it's proportional linearly. The magnetic field intensity is proportional linearly with R, so you have a straight line goes from 0 to here. So when R equals to A, this is simply J sub 0 A over 2, like this. On the other hand, if R is greater than A, then the magnetic field intensity becomes smaller and smaller as the distance R gets further away from A. So you have this curve. It's concave up. 那个弯曲朝上的叫 concave up. Okay. All right. So that should conclude our discussion.